Hi everyone, my name is Dirk and I'm a senior research engineer at the Allen Institute for Artificial Intelligence. I'll start by giving you a brief overview of the AllenNLP library and why we're building it the way we're building it. After that, I'll move on to what's next for our team, combining natural language with other modalities, starting with vision. For those of you who don't know, AllenNLP is a library and framework aimed at researchers. It started as an in-house tool for solving common tasks in natural language research, and has grown into kind of a toolkit that researchers use for their work. Some people even put it in production. The core of the library is, of course, the pieces that it consists of. I put some of the components you will find on the slide here, but it's not an exhaustive list. Some of the things in here are hard to get right, like a distributed trainer or beam search, but a lot of it is not. Calculating F1, how hard could it be? It's not, but there are annoying details, like making it work in a distributed setting, making it work with the same APIs the other metrics use, making training decisions based on it, and so on. Another example, downloading and caching a file is pretty easy, right? Well, the devil is in making it robust. What about e-tags for cache invalidation? What about downloading files from inside compressed archives? What happens when we're offline? For all the code that goes into the core library, we're trying to go the extra mile and make it work in more circumstances than the one we're facing right then. The point I'm making here is that this is not research code. As you might know if you browse or even try to use GitHub repos from research labs, researchers often, but not always, tend to write exactly the code they need to get the paper published and no more. A lot of the work that happens in my team is to take that code and make it robust, maintainable, and even reusable. To ensure this, we use all the things that are normal in industry but unusual in research, like code review, type checking, automatic tests, generated documentation, and so on. That extends to our models too. We have models for many standard tasks, and we like to think they're well-engineered, reusable, and a good example for how to write model code. They are trainable out of the box if the training data is freely available, and many of them have a demo at demo.allennlp.org. The obvious benefits of writing code this way are reusability, maintainability, ease of use, but since AllenNLP is open source, there is another benefit of it as well. It can function as a template for new work. A lot of progress comes from combining ideas or trying variants of existing ideas. We see it as an explicit design goal to enable a scenario where someone copies the whole code base, makes some tweaks to a model or a component, and runs some experiments. Sometimes, though not as often as I would wish, they contribute back their findings and everyone benefits. To support this further, we have template repositories up on GitHub that you can use to get started right away. There are actually two template projects on GitHub. One is using the library like a library, but the other one is using these configuration files. The text on the right is a JSON file that specifies the data to use, the model and how to configure it, and how to train it. AllenNLP comes with a command line that can run a config like this, and for many people, this is the normal entry point to AllenNLP. JSON, by the way, is a superset of JSON. You can think of it as JSON plus variables, but it can actually do more than that. By the numbers, this is actually the more popular way of using AllenNLP. I personally prefer code, but many people really like having their whole experiment spec laid out in one file like this without a lot of distractions. That's it for my brief overview over AllenNLP. We have a bunch of material online to get started, so I don't want to spend any more time on this here, but if you want to know more, check out any of these links. So after we released version 1.0 in May, we considered several themes to pursue for a 2.0 version. The world was our oyster, so to speak. And we settled on tackling the problem of combining natural language with other modalities. BERT solves a lot of pure text tasks already, but what if you want to answer questions about an image, a piece of music? What if you want to query a knowledge base? There were many reasons for choosing this as a theme, but mainly we observed what kind of research was already being done internally and what people were talking about doing in the future. Also, the prior team is one of the top labs for computer vision, and they are part of AI2. It seemed obvious then to start with images and videos as the first step. Before I go into details about what exactly we're building, let me spend 2 slides on why we're building it. There's a bit of a debate going on about whether the world can be understood through text alone. A baby locked in a room with a printout of Wikipedia won't develop intelligence. On the other hand, computers are not babies, and airplanes famously don't fly the same way that birds do. Rather than getting mired in a philosophical debate, let me offer some practical reasons why this is important. We will want to build systems and ultimately products that combine speech with other inputs. A domestic robot might need to know what and where a refrigerator is when instructed to fetch something from it. It might want to communicate about its own battery status or ask for help if it's stuck. Combining text with other modalities might feed back and improve pure text capabilities too. For example, we have a project at AI2 that tries to learn a more generally useful transformer model by training it on vision and text tasks jointly. Airplanes notwithstanding, this is after all how children can acquire so much language with so little input. This might be a good moment for a shout out to GPT-3. Before GPT-3, I was firmly in the camp of text is not enough, but now I'm not so sure anymore. So let's talk about what we're actually building. This is a crude simplification of the AllenNLP processing pipeline. I'll add stuff to this as we go along. It's pretty straightforward. The dataset reader reads a dataset and turns it into instances. These instances are fed to the trainer, which in turn turns them into batches and feeds them into the model. For text, I think most people know how this works. We read the text from a file, tokenize it, assign integers to the tokens, maybe add some special tokens, and put the whole thing into a tensor. But how does it work when the dataset contains images? The first step of that process is image loading. This is pretty boring, so I won't spend too much time on it. It basically takes a file name and returns a tensor that contains each of the pixels as a triple of floats, one for each color channel. Under the hood, this is not completely boring, since this thing reads multiple formats, normalizes color spaces, rotates images if so specified in the EXIF tags, and so on. But we're just using a third-party library for it, so it's not that interesting for us. The important thing is we get a tensor out of it, and now the action starts. What we want to do is featurize the image and bring it into a format we can use in a downstream model. Right now, we're implementing two ways of doing this. The first one is to run object detection over the image to find so-called regions of interest, and then create an embedding for every one of these regions. In this example, we found 5 regions, so we end up with 5 embeddings. We stack those embeddings so that the whole image is represented as a tensor of 5 times the embedding size. Clearly, the number of regions can vary from image to image. We also throw in another tensor for the positions of the regions, so now every image can be represented by these 2 tensors. That is one abstraction that we offer, and we call it region detector. It would be pretty useless if we provided only the abstraction with no concrete implementation. So the first one of these region detectors is based on faster RCNN by Ren et al. Optionally, there's another thing region detectors can return, and that's a distribution over object classes. Basically, this is a vector for every region that gives us a probability that the region contains a certain object. For example, the region in the top left of this image should have quite a high score for the object of person. Not every region detector returns these numbers, though. The other way of featurizing an image is to not worry about regions at all and just use a grid where every grid square gets an embedding. Obviously, this is much simpler, but the jury is out whether you can get the same quality of results by doing this. This is one of the experiments we hope to enable with our framework. We call this a grid embedder in the API, and we're offering ResNet as a default implementation. The next question we have to answer is, where in the pipeline do we do this? There are 2 choices, each with benefits and drawbacks, and we support them both. The obvious choice is to run them in the dataset reader. The main advantage of doing it there is caching. AllenNLP can cache the output of the dataset reader and reuse it later. Featurizing the images is a pretty heavy operation, and so caching the output can save quite a bit of time. If you're just training straight through once, the cache only helps from the second epoch onwards. But given the way we work, this scenario is rare. The cache is much more effective when you are experimenting with the model and you're running many different configurations that can reuse the cache from one training run to the next. There's a second kind of cache, but it requires a bit more work. We noticed that the same images often appear in multiple instances and even across datasets. In this scenario, caching instances does not help. So we developed something called a tensor cache, which is just a fancy word for a key value store where the keys are strings, usually file names, and the values are tensors. This cache works across processes, even with multiple processes at the same time, so we can use it in a distributed setting or with multiple training runs simultaneously. This cache is not specific to image tensors. It could be used for anything, so if you want to steal it for your own project, go ahead. So that's it for featurizing while reading. The other way of running it is featurizing while training. You cannot cache the featurized images if you do that, so why would you? The answer is that you want to fine-tune the image featurizers themselves during training. We made sure that all the featurizers are instances of torch.nn.module, including the pre-trained ones, and can be trained like any other torch module. For a grid embedder, you can kind of see how this works. You can imagine that each patch gets run through some network, probably a variation of CNN, to produce a vector. But for a region detector, how does this work? Selecting the coordinates for a region is not differentiable, so how can you train through it? The answer is, of course, that you can't. Internally, the region detector detects a bunch of regions, orders them by how interesting they are, and returns the best ones. Taking the top n is not generally differentiable, so we can't train through it. But we can still fine-tune the steps that come afterwards, i.e. creating embeddings for the regions. At the time of recording, the plans for how to do this have not been finalized yet, so I can't be completely forthcoming with details. The solution will probably involve splitting the region detector in two, so that detecting the regions can be done in the reader, but embedding the region can be done during training. The other reason why you might want to featurize the images in the model is that you might never see the same image twice. This might happen due to data augmentation, where the same image is subtly altered every time it's presented to the model. Here are some examples of transformations we can do to the images. We can play with the colors, crop it, flip it, rotate it, sharpen it, and so on, in ways that would not change the answer in the downstream task. We would do this to help the model generalize better. Since the model never sees the same image twice, it cannot overfit to the images, at least not in simple ways. This is another area where at the time of recording this talk, we have not finalized the design, so I will leave it at that. Maybe ask me after the talk how far we got with it. So that's a lot of stuff about images, but this is the NLP Summit, so where's the natural language? The natural language has been there all along. To build a model that performs, for example, visual question answering, you would treat the question the same way you always do in AllenNLP. You tokenize it, you index the tokens, you run the resulting tensor through an embedder, which is usually a transformer now. At this point, you have embedded language and embedded images, and you can start writing a model that combines them. We don't place any restrictions on what you can do with them, but we offer one feature called the Transformer Toolkit. Before I explain what that is, let me motivate it. In this example, we have two images and the question, what color is this bank? The meaning of the word bank changes depending on the image. Ideally, you would get a different word embedding for it in the two different cases. How do we accomplish this? It's an open research question, but we want to enable at least one avenue of experimentation. One text plus vision model does this by essentially running two transformers in parallel, one for vision and one for text, but interspersing layers that allow them to communicate. The Transformer Toolkit is a set of modules that lets you experiment with architectures like this easily. In this example, you would use it to instantiate a torch module that consists of the BERT embedding layer plus the first two self-attention layers. On the vision side, you do the same thing, except there are no pre-trained weights in that case. Then you run a self-attention layer that combines the input from both sides. You can write that yourself or potentially use another component from the Transformer Toolkit. Then you run a few more BERT layers and then another combining layer. You can do this by taking modules out of the Transformer Toolkit and combining them in new ways without writing a lot of code yourself. This slide is a simplification of the Wilbert architecture by Liu et al. Jocelyn Liu is a contributor to this project, so we will have a complete Wilbert implementation in the final version. I'm only showing one way of using the Transformer Toolkit here, but there are other things you can do with it. Some people have put memory layers somewhere into the stack. Some people have switched out the layer norm that's hidden inside a complete BERT layer. Some people experiment with tying weights between the layers. One of my favorites, the universal transformer, decides for every instance how many layers to run, so it can stop early if it's already done. With the Transformer Toolkit, we want to make it easy to play with these things and do so on top of the existing pre-trained weights. We're doing it motivated by this vision plus text architecture, but most of the experiments I mentioned are actually pure text experiments. I'm hoping that this work will be useful beyond our ambitions of combining text with images. Another area that's not specific to vision is multitask learning. Multitask learning is particularly important because one of our contributors uses it to train better image understanding models. We wanted to take his design and generalize it so all areas can benefit, not just computer vision. Without departing too far from the existing structure in AllenNLP, this is what we came up with. First, you write a reader for every one of the datasets you want to use. Then you configure this supplied multitask dataset reader to use the readers you wrote, giving each of them a task name. I use colors instead of task names on this slide. The multitask dataset reader reads the instances from all the readers and attaches the name of the task to every instance. Over on the model side, we read those task names out of the instances and change our behavior accordingly. The multitask model consists of two parts. The backbone is the part of the model that runs on all instances regardless of task. You have to write this part yourself since it's dependent on what you want to accomplish. For example, if we're training BERT to do question answering and sentiment analysis at the same time, the backbone would be BERT because it's the part that is common to the two tasks. Then, depending on the task, we run one of the model's specific heads. In our example, we would have one head for question answering and another for sentiment analysis. The multitask model selects the correct head and sends the output of the backbone there. It then takes care of scaling the loss appropriately and reporting it back to the trainer. The final piece of the puzzle is multitask data loaders. I haven't talked much about data loaders before. Normally they determine things like batch size and batch composition. In the multitask setting, they do that too, but they also decide what tasks to send to the model next. To make this decision, we have something called a multitask scheduler. The purpose of the multitask scheduler is to decide at any given moment which tasks to send to the model next. There are a few obvious candidates for how to do this, and I've put those on the slide. Explicit schedule means you can just write out the sequence of tasks you want to use, and it will execute that sequence over and over again. Special shout out to dynamic stop and go. That's an algorithm from one of our contributors. It performs regular evaluations on the dev set to find out which tasks are done training and which ones need to train more, and then uses that information to decide which tasks to schedule next. That's a gross simplification, and for details, I encourage you to read the paper. Either way, we think our APIs will be flexible enough to allow this, but the code for this is not written yet, so I can't promise yet that it will be in the final version. There are some things I can firmly promise though, because some of them even made it into 1.0, and that's performance fixes. Computer vision datasets tend to be much bigger than most NLP datasets. The COCO dataset is 27 gigabytes in size. The VQA dataset that uses those images has 1.1 million questions. So we had to step up our game when it comes to performance. Even in version 1.0, we already shipped multi-process training. In Python, using multiple processes to feed multiple GPUs is faster than doing it from a single process, mainly because Python is a stupid language for machine learning. For now, though, it's the language we're stuck with, so we did the best with what we have and implemented it. We also already shipped gradient accumulation and gradient checkpointing. Those don't make training faster, but they make it possible to process larger batches on smaller GPUs. FP16 is really cool, mainly because many GPUs have special cores to deal with 16-bit floating point math. This does affect the quality of the results, so it's disabled by default, but in AllenNLP, you can just flip a switch, turn it on, and try it. Finally, we had to work on our caching. What we had was fine when every instance is a little bit of text, but it's not fine when an instance can be multiple megabytes of image data. We have no plans to implement training on multiple machines. We have fairly big single machines in AI2, so we don't have a lot of internal need for it. But our multiprocess implementation uses PyTorch's multiprocessing, which already supports multiple machines, so it's not a big stretch to do it. If you feel inspired, please tag me at DirkGR in the pull request. Finally, we're putting it all together by implementing dataset readers for common language and vision datasets and models that solve their associated tasks. This is a list of the dataset readers we want to write and the tasks that they address. Let's look at some of them in detail. Here's an example of visual reasoning from the NLVR2 dataset. An LVR2 always gives you two images in a sentence, and the model has to answer either true or false. This is not a lot of supervision per instance, just one bit. So a model will almost certainly have to rely on pre-trained knowledge. Image captioning is exactly what you think it is. You're given an image and your model has to produce a natural language caption for it. This example is from Google's conceptual captions dataset. Here's an example from VQA v2, a visual question answering dataset. In VQA v2, many questions have multiple correct answers, and the answers are usually short, so that makes it a little bit easier. Referring expressions means you're given an expression and you have to predict the bounding box that contains the object referred to by the expressions. The last kind of dataset we're thinking about is visual entailment. In this kind of dataset, you're given an image and a sentence, and the model has to decide whether the sentence is entailed in the image or not. How many of these we actually get done remains to be seen, but it's not a lot of work to write one more, and it's kind of fun to do, so we might just do them all. In summary, this is a list of things we're building into AllenNLP. Since we're recording this almost a month before the actual conference, I have good hope that by the time this airs, most of these things will be ready for use. For more information, go to any of these places or ask me directly either now or later via GitHub. Before I stop, let me give a quick shout out to the team. The people in the bottom right are not the whole team, they're just the ones that come to stand up. They are also the ones likely to help you on GitHub or wherever you choose to contact us. The whole team is big and fuzzy around the edges, as I think is the case with many open source projects, so it's impossible to put them on a slide. Thank you very much.